All right, so yesterday we did section 11.1, which is on sequences. And the goal there was to basically figure out a pattern so we could predict the next term in the sequence or even a term that's much farther down in the sequence. In 11.2, we're going to talk about what a series is. So a series is when you add up all the numbers in a sequence. And if you have a very short sequence, like it's only 5 or 10 numbers, that's not bad. You can just add that up by hand. But what if you had a sequence that had 50,000 numbers in it? And I said to you, what do they all add up to? Well, we don't want to have to add up 50,000 numbers by hand. So in this section, we're going to figure out a quick way to add up all the numbers in a sequence. Some sequences stop, right? Any sequence that stops, you can theoretically add all the numbers up. Even if it did have 50,000 numbers, you could do it, or you could program a computer to do it. Even if it had 50 million numbers, you can add that up. But what gets a little bit more interesting is adding up an infinite amount of numbers. Right? You might think, well, how could you do that if you just keep adding and it never ends? Well, sometimes you can and sometimes you can't. It depends on what kind of numbers you're adding. So it is possible that you add up an infinite amount of numbers and you get very close to an answer, right? Like it approaches an answer, like an asymptote, right? And then sometimes you add up an infinite amount of numbers and it doesn't. It just keeps adding up and getting bigger and bigger and bigger. Right? So we'll talk about that more tomorrow. All right, so in the last section, we use this notation to denote a term in a sequence. Usually we replace the n with whatever term you want to know. Right? So a sub 1 would mean the first term in sequence A. A sub 2 is the second term. So let's say that we had this formula. Okay? So somehow we had a sequence of numbers and we figured out that that was the pattern for it. It'd be a little hard to figure out that pattern by hand because it's doubling the number, subtracting 1, and squaring it. It's a little more complicated than one that I would give you to figure out. Right? But you don't have to figure it out. I'm giving you the formula. Let's write down some of the terms in that sequence. So let's do term and position. Let's start. Let's do the first 4. Okay, if we plug in a 1 for n, what's 2 times 1? 2. Take away 1. 1. And then if you square it, 1. Right, let's do 2. 2 times 2 is 4. 4 minus 1 is 3. What's 3 squared? 9. Let's plug in 3. 2 times 3 is 6. 6 minus 1 is 5. And what's 5 squared? 25. So just remember what this was. That was 1 squared, 3 squared, 5 squared. Anybody have a guess what the next one is?
7 squared.
It's going to be 7 squared. This is basically odd numbers squared. That's what ends up happening. All right. Now we're going to look at something a little bit different. We're going to look at this. S sub n. When you write a capital S, when you put a sub n, like that, that means to take the terms in your sequence and add up the first 3, or the first 2, or just the first 1. Okay, it means to add them up. So S sub 1 means to add up all the terms up to the first term. What do you get if you add up every term up to the first term in that green box?
1.
Just 1. Yeah. It's basically just the first term. S sub 2 means to add up all the terms up to the second one. What do you get if you add up everything in that green box up to the second one? 10. S sub 3 means to add everything up to the third term. What do you get if you add up everything up to the third one? 35. And what we've just created here That's a new sequence of numbers, 1, 10, 35, and we could keep going. If we added the next one, we'd add 49 to it. This is what we call a sequence of sums. So now, if we can figure out a pattern for the numbers in the red box, then we could add up as many as we wanted. Right? I certainly wouldn't want to try to do S sub 500 this way. Right? I don't want to add up 500. I don't even know all 500 terms, first of all. And second of all, even if I knew them all, then I'd have to add them all up. Right? The goal is going to be to find a pattern for the numbers in the red box. Then we can figure out anything we want. Okay? And then I kind of broke it down. I guess I just broke it down in more detail compared to what we did up above. So the first one was just 1 squared. The second one was 1 squared and 3 squared. The third one is 1 squared, 3 squared, and 5 squared. And the fourth one would be 1 squared plus 3 squared plus 5 squared plus 7 squared. That's how you find those. Okay, so any questions on how I got those formulas for each one of those? And then the actual answers I put up in the red box up above. Okay. Let's see. So, in general, this last one is what do you get if you add up the first n terms? This is the first 1 terms, first 2 terms, first 3 terms. That's the first n terms. So it's the first one, the second one, the third one, the fourth one, fifth, sixth, seventh one, all the way up to the nth term. What is the nth term? Well, I don't know. It could be as high as you want to go. Maybe it's the 700th term. But this dot, dot, dot represents adding up a bunch of things. We didn't write them all down, so there's a big gap there. So first term, second term, third term, fourth term, maybe it's the 100th term. In order to actually figure out a number, you would have to know what that is. You would have to know, well, what is the nth term? Are we stopping at 100? You're going to add up the first 100? You're going to add up the first 5,000? You got to know that. And that's something that I would give you. So each one of those things that we found on the other page, S1, S2, S3, that is called a finite series. Anytime you see the word series, if the word series confuses you, you can basically think of the word series as the word sum. Okay, so each one of those things we just found was a finite sum. And the reason it's finite is because it didn't go on forever. It had a stopping point. Like, that's S2. 1 squared plus 3 squared, stop. There's nothing else. S3, 1 squared plus 3 squared plus 5 squared, stop. So now, once you figure out those partial sums, 1, 10, 35, what's in that red box is that. 1, 10, 35, that is called the sequence of partial sums. And that's what we want to try to find a pattern for. What's in that red box. Okay, finding a pattern, like how do you predict the next, all these numbers in the red box? That can be a little tricky, so we're going to go over some common formulas that come up. Generally, it's not as easy as getting like the kind of formula we did yesterday, where you have like the arithmetic or geometric, and you just have a formula you have to plug into. It's not quite as easy as that. Right. Here's another example of a sequence of partial sums. Right. Let's say we had this formula. A sub n equals 2n plus 1. Let's just write out the first 5. Okay. If you plug in 1 for n, what would you get for your term? 3. What if you plug in 2? 5. If you plug in 3? 7. 9. And 11. Okay. Now, those are the terms in the sequence. Now, let's see if we can find the partial sums. Okay. What do you get, just focusing on that red box, if you add up the first 1 terms in that red box? 3. How about if you add up the first 2 terms in that red box? 8. If you add up the first 3 terms in that red box, you would get 15. The first 4 terms would give you 24. And the first 5 terms would give you 35. So now, write those numbers down in a sequence. 3, 8, 15, 24, 35. That is a sequence of partial sums, where each number in the sequence represents a bunch of things that were added up to get that number. Okay? And that's the goal. Can you predict the next term in that sequence using a formula? Okay. So, any question how I got that sequence of partial sums? And the reason they're called partial is because it's not all of them. Like, it's just the first 1 terms, or just the first 2, just the first 3, just the first 4. It's just a certain amount represented in each one of those. It's not all of them. If you tried to add them all up, it would just add up to infinity in this case. Because each time the number that you're adding is 2 bigger than the one before it. So the terms in the red box are just going to grow bigger and bigger and bigger. And if you keep adding numbers up that get bigger and bigger, your answer just keeps getting bigger and bigger. All right. So this would not be a good one to look at if we wanted to add up an infinite amount of terms. Okay. Which is why we're only looking at adding up some of them. Okay. So writing this down can start to get pretty long. All right. Like if I wanted to add up S50 using this notation, I would have to say the first term plus the second plus the third plus the fourth, all the way up to the 47th, the 48th, the 49th, plus the 50th. That's a lot of plus signs to write out. So there is a shorter way of expressing this idea. Right? Rather than writing we want to add up and writing it all out like that, we can use what's called sigma notation. Okay. In sigma notation, you're going to see that symbol, which is a capital Greek letter, sigma. And there's going to be 3 things around that sigma that basically tell you what you're doing. So let's take a look at that. Here are the 3 things I was talking about. So this over here is going to be a formula. it's going to be telling you how the numbers you're adding up are being generated, right? It's the formula, like that we learned yesterday. This is going to tell you basically a starting point. Okay, you want to add up a bunch of numbers in the formula? Okay, fine. Where do you want to start in the formula? You want to start at the first number? You want to start at the sixth number? Where do you want to start adding them up? This is where you're going to stop. Okay, so you got a starting point, a stopping point, and then you have the formula that's going to be generating the numbers that you're adding up. The way you pronounce this, the capital sigma, you pronounce as the sum. So that part right there is the capital sigma. So it's the sum from, and then you read the starting number, where you're going to start, and then from the start to the stop. So you're going to start here, you're going to stop here, and then you read the formula that you're using to add your numbers up. Okay, so let me show you an example. This particular problem is going to be adding 5 things together. You're going to start with a 1. You're going to stop with a 5. This is the formula that you're using to generate the numbers you're adding up. Think of 1 as like the start position, and think of 5 as the stop position. So we're going to plug in every number from 1 to 5, one at a time. We're going to add them all up. We're going to plug them into that formula. All right, so the way you do this is you start with 1. What's 2 times 1? 2, and then plus 3? 5. Okay. That's what you get when you plug in 1. Now, go up to the next spot. 2. So let's plug in 2. What's 2 times 2?
4.
And 4 plus 3? 7. You're going to keep going until you reach the number at the top. All right, so now we go to 3. What's 2 times 3?
6.
Plus 3? 9. All right, we got the top number yet? No, we just did 3. Okay, go to 4. What's 2 times 4?
8.
And then plus 3?
11.
11. We got the top number yet? No, one more. Now we go to 5. What's 2 times 5?
10.
And 10 plus 3?
13.
13. Now we'd say, okay, the next number would be 6. But they said stop at 5. So what you have on the left means to do what's on the right. And then you could actually add those up and see what you get. So this is called, on the left, that's sigma notation. And on the right, that's expanding it all out and showing the numbers you're actually adding up. So plug that number into your formula, the bottom number, write it down, and keep having this number on the bottom go up by 1 until you get to the top number. And that's when you stop. Any question on how I wrote that down? Bless you. So here's the difference between the two notations. Kind of the same thing I just wrote on the other page. The top one is sigma notation. When you actually plug the numbers in and start doing it out, and then you have individual terms you're adding up, like I do right here, that's called expanded notation. So if you see directions that say expand the following sum, it means to do what I did on the bottom of this page on the left. That's called expanding the sum. All right, let's try expanding another one. just see if we can do that. Now, this time, you're starting with what number that you're going to plug in for k?
1.
You're going to start with 1. And what's the last thing you're going to plug in? N. We don't know how high n is. So when we don't know, or we don't have a number for that top one, I would say do the first 3. Do 1, do 2, do 3. You've shown me the pattern. And then we'll do like ... And then we'll jump to plugging in n as the last one. Right. So let's start with 1. 2 times 1 is going to give me 2 plus 3, 5. And let's just leave it as 5 squared. Okay, so that's the first one, 5 squared. Let's go to the next one. Let's plug in 2. What's 2 times 2?
4.
Plus 3?
7.
So that's 7 squared. Plus, let's do one more, 3. What's 2 times 3? 6 plus 3? 9 squared. And now there might be a bunch more we don't know. Now let's jump to the very last number. The last thing we're going to plug in is n. We don't know what n is, but it would be a number. The point is it stops somewhere. If we plug in n, what's 2 times n?
2n.
And then plus 3. So it's 2n plus 3 squared. That would be the very last number if we knew what n was. So that's how you expand the sum. Okay. When you don't know the top value, just do the first 3 and then jump to the last one. If you know the top value, then that's fine. Then do it all out up to that top value until you finish. If you wanted to write these out as 25, 49, and 81, you could do that too. The reason I didn't write it that way is because if I don't square them, I think you can see the pattern better. It's odd numbers squared. 3, 5, 7, 9. The next one would be 11 squared. Okay. Any questions on that? All right. So let's look at a few different properties of these sigmas, these summations. Okay, we're basically going to look at how you can take 2 different sigmas and either add them or subtract them. It's basically combining like terms. Okay? The proper way to draw the sigma, if you really want me to do it perfect, it should look like that. But the faster I go, they start not looking as good. Okay, but that's how it should look. All right, let's start with this one. So this first one is giving us a rule for taking 2 sigmas and adding them together. I think it makes more sense if I actually do this with some numbers so you can see it. Let me make up 2 sequences. Very short, very simple sequence. So A sub k is going to be the sequence 1, 3, 5. B sub k is the sequence 2, 4, 6. What I want to do is add these sequences together. And this formula is basically saying there's 2 different ways to do it. Let's do it the way that's on the left first. The way that's on the left, it says to first, in parentheses, add the 2 sequences together. When you want to add one sequence to another, you add them term by term. Okay. First term to first term, second term to second term, and so on. So let's figure out what's underlined in red first. If you add the first term in each sequence, what number do you get? 3. The second term in each sequence? 7. And the third term in each sequence? 11. Okay, so that's the part underlined in red. Now, when you have a sigma, That means to take everything you got from that last step and now add that all up. So the sum of what we just did is going to be 3 plus 7 plus 11. That's what that symbol means, to put a plus sign between each number that you just found. Okay. And in our particular case, we started with the first term, and we stopped with the third term. There were only 3. Okay. What's 3 plus 7 plus 11? 21. Okay. So that's doing it the way that's on the left. You get 21. Now let's do it the way that's on the right. The way that's on the right says before you combine the sequences together, add the numbers up in each sequence separately. So let's do the sum of every number from the first one all the way to the third one of a sub k. What's the first number in a sub k? 1. Second number? 3. And the third term? 5. What do you get if you add up all the numbers in sequence A? You get 9. Okay, that's this part right here. 9. Now, let's do it again, but for sequence B. Let's add up all the numbers there. Starting with the first term and going to the third term. What's the first term in sequence B? 2. Second term? 4. And third term? 6. What's 2 plus 4 plus 6?
12.
Yes. Gives you 12. That's the second part. So we added together all the numbers in sequence A first. Then we added all the numbers in sequence B. And now we're going to add those two together. What's 9 plus 12? 21. So the point is you can do it either way. Right? If you want to add up all the numbers in 2 different sequences, you can either add them together term by term and then add that, or take the first sequence of numbers, add up everything you have, take the second sequence of numbers, add up everything you have, and then add those 2 numbers together. Now, if this rule applies for addition, what other property do you think it also applies for?
Subtraction.
Yeah, you could do exactly the same thing with subtraction. I'm not going to go through the whole thing all over again, but you could. So property 1 has to do with addition. Property 2 has to do with how do you subtract one sequence from another sequence. And property 3 is how do you multiply every sequence, every number in a sequence by a value. Okay, so let's take a sub k again. And let's say I want to quadruple that sequence and add everything up. There's always adding involved. Okay, so I want to quadruple every number there and add it all up. One way I can do it is quadruple each number first and add those up. Or I can add them up the way they are and quadruple it after. Okay, that's the difference between the 2 ways. So I'm going to make up a number for C. Just because I said quadruple, so we're going to multiply it by 4. Let's do it the way on the left first. Let's find this. That means to multiply every number in sequence A by some value. In this case, it's 4. What do you get if you multiply each of those by 4? 4, 12, and 20. That's sequence A quadrupled. 4, 12, 20. Now, let's add up. That's what that symbol means. Add up every number that you just found. From the first one to the third one. Okay, the first number is a 4. Next number is a 12. Last one is a 20. What's 4 plus 12 plus 20?
36.
36. So if you want to quadruple every number and add them up, and you do it that way, you get 36. Now let's try it the way on the right. The way on the right says add all the numbers up first. Okay, you always do what's in the to the right of the sigma first. So let's add everything up. So the sum of the first 3 numbers in our sequence. So go back to this. 1 plus 3 plus 5. Yeah, adding up every number in sequence A. I am not using sequence B for this. I don't need it. Because this isn't about adding 2 sequences together. It's about multiplying a sequence by a number. Okay, what do you get if you do 1 plus 3 plus 5? You get 9. Okay, so this part right here that's in the green box, we just got 9. Now, what's the value that we used for C in this problem? 4. So there's still a 4 in front of the green box. 4 times all the numbers we just added up. What's 4 times 9?
36.
36. And how does that compare to the other answer we got? What?
Match.
Yeah, it's the same thing. All right. So if you wanted to quadruple every number in a sequence, you could quadruple each one of them first and then add them up. Or add them up before you quadruple them and then quadruple that answer at the end. But you get the same thing either way. Yeah.
How do you get 4 for Stephen?
I just made that up because I said quadruple. So if it was triple, C would be 3. If it was double, C would be 2. Yeah. So the important thing here is anytime you want to multiply a sequence by a number, that C can end up going in front. And that's what we're going to want to do. We want the part that's circled here to be as simple as we can make it. Multiplying it by a number makes it more complicated, but we don't need to have the multiplication there. We can move the C to the front, and it won't affect the answer that you get. Okay. So any question on those 3 properties? All right. So let's try combining these into a single sum. First thing, which I don't think I specifically pointed out, but when you are combining together, they have to have the same index. Okay, that bottom number is called, that's the starting value. If one starts at like a 2 and the other one started at a 1, you can't combine that. They have to start at the same and they have to stop at the same to combine them together. So when we recombine them, what's going to be the starting point based on the formula we have up there when we put them back together? Yeah, it's exactly the same as the other ones. So it's going to start at 1. And what's going to be the stopping point? N. Okay, it's going to be exactly the same. Excuse me. Thank you. It's going to be exactly the same as the ones you had in the problem. Now we just combine basically this part to this part. Okay, think of that one that I circled on the left. That's like your A sub k. And the one on the right is your B sub k. So write down what I just circled right there. But instead of A sub k, write 5k squared minus 4 plus, and instead of B sub k, write 7 minus 2k plus k squared. And then just combine your like terms. So instead of doing two different sigmas, we can combine them into one once we combine like terms. Okay. Is there anything I can combine the k squared with?
5. Okay, squared.
Oh yeah, thank you. I forgot to write that. So that's a 5k squared. What's a 5k squared plus a 1k squared?
6k squared.
6k squared. So we took care of that and that. How about this negative 2k? Is there anything I can combine that with? No. So we got that. How about a positive 7 and a negative 4? Positive 3. Yep. There you go. So doing what we just circled there is exactly the same as doing those two separate summations at the top. It's just that's a faster way to do it because you're only doing one problem instead of two. All right, so generally that's how you want to do it. You basically want what's on the left. That's simpler. That's 1 versus 2. All right. Any questions on that one? All right, let's try, so we'll call that example 2A. Let's do one more of those. Let's do 2B. Same directions. Let's do, sigmas are getting pretty bad. So k equals 1 to n. Let's do 2k squared plus 3k minus 4. And let's add that to, let's do k equals 1 to n of k squared plus k minus 5. Okay, when I combine those two together, what's going to be my start? 1. Okay, so we'll start at 1. I'm going to stop at n. And let's start with our k squareds. How many k squareds do we have? Yep, so 3k squareds. How many k's? 4k. And my constant. -9. Yep. And that's it. So I would say the bottom one is simpler because it's one problem versus two. Any questions on that? All right, so writing things using this symbol, okay, sigma, is fine. It gives you a compact way of explaining what you want to do. But if I wrote this down, and I wanted you to do that out, it doesn't give you a quick way to actually do it. Okay? What I'm saying here is I want you to plug in every number from 1 up to 500 for k. As you plug in each number, I want you to write them all down, what you get, and then I want you to add them all up. So it's a short way of saying what I want you to do, but actually doing it is still going to take you forever. Okay? So what we want to be able to do is get rid of the sigma symbol. And for certain patterns, we can do that. Okay? I'm going to show you, I think, two patterns that come up that we can get rid of the sigma symbol. In general, that's not easy to do, to try to get rid of the sigma. Okay? That could be hard depending on your formula. Okay, so let's look at this one. This one is saying, even though it's not that bad, it's still going to probably take most people more than 5 seconds to do that. It's telling you to plug in every number from 1, stopping at what number?
10.
10 for k. It's not even a complicated formula, but it's still going to take you a while to do it. It means to do this. That's what they want you to do. Or even just writing it down took me at least 5-6 seconds. Never mind adding it all up now. me
55.
see if I can put the plus 10. Yeah, there are certain tricks you could use. For example, if you're good at recognizing patterns, you have to add all these up. So it doesn't matter the order you add them in. What do you get if you add 1 to 10?
11.
11. How about if you add 2 to 9?
11.
11. And what if you add 3 to 8? 11. So you're basically just adding up a bunch of 11s. You just have to figure out how many are there, right? There's another one there, and there's another one there. So there's 1, 2, 3, 4, 5 groups of 11. So yeah, it's going to be 55. Yep. That's great that that little trick works here, but sometimes it's not that easy to come up with that kind of trick. So we're going to figure out a better way than even having to do something like that. Let me write down what these add up to. Let's just do some of them. So we got 1. What's 1 plus 2?
3.
3. What's the first 3? 1 plus 2 plus 3?
6.
6. How about 1 plus 2 plus 3 plus 4?
10.
And let's do one more. 1 plus 2 plus 3 plus 4 plus 5?
15.
15. Okay. I want you to look at that. Okay, you don't know how I came up with that maybe, but that's okay. So here's the term. Here's the position. Remember, each one of these terms represents a sum. Like this is adding up the first 2, first 3, first 4, first 5. Let's plug in 4 to that formula, and let's see what we get. What's 4 plus 1? 5. What's 5 times 4?
20.
20. And 20 divided by 2?
10.
10. Let's plug in 5. What's 5 plus 1?
6.
6 times 5?
30.
And what's 30 divided by 2?
15.
15. So now, if you said to me, what if you went all the way to 100? And you said, what do the first 100 numbers in that pattern add up to? I could just go into this formula and say, the first 100 numbers is going to be 100 times 101 divided by 2. Or 50 times 101. So it's very easy to add up the first 100 numbers, but it's only because I gave you that formula. All right. So we're going to write that down a little bit more formally on the next page, but this n times n plus 1 over 2 is a very quick way if you want to add up integers, like 1 plus 2 plus 3, as high as you want to go. That formula will give you the answer. So if you want to add up every number from 1 to 10,000, just plug in 10,000 for n, and you'll get your answer. And that's a lot quicker than doing 1 plus 2 plus 3 plus 4 all the way to 10,000. So we're going to look at, when I say some formulas, I mean 2. We're going to look at 2 formulas that allow you to take something that's a summation, like that, and convert it more into something like that. Okay, the one I showed you already, that's the most complicated one. That's as complicated as we go. But let's look at one that's been a little simpler. Let's say I wanted you to do this. This time, your formula on the right-hand side doesn't even have a variable, just a constant. So where's the k in that formula? Like over here, you had the k right there. Where's the k in that formula?
Would it be a subscript?
No.
Is it 3?
Well, k is a variable. Is 3 a variable? No. So it's not the 3. So where's the k?
It's not there.
It's not there. There is no k. So when you plug in 1 for k in that formula, what do you get? 3. How about if you plug in 2 for k in that formula?
3.
You get 3. Okay, keep going. What about when you plug 3 in for k? How about when you plug 4 in for k?
3.
And how about when you plug 5 in for k? 3. So the number on the right-hand side never changes because there's no variable attached to it. You're adding 3 plus 3 plus 3 plus 3 plus 3. What's a short way of saying that?
3 times 5.
You're adding up that number that many times. So whenever that number on the right-hand side is a constant, the answer to doing this whole thing out is going to be that number multiplied by that number. So now, looking at this one, let me make this page a little bigger again. What do you think the answer to this would be? It's the same thing we just did, except it's not a 3 and a 5. This time it's a c and an n. Yep. It would be c times n. Exactly. So if you have to add up a constant, which is something without a variable, and you have to do it that many times, it's going to be c times n. You just multiply those two numbers together, and that gets rid of the sigma and gives you a nice number for the answer. Okay, and the only other formula that we're going to look at is the one I already showed you. If you have to add up integers, okay, this formula is just a k, meaning you're adding up like 1 plus 2 plus 3 plus 4, as high as you want to go. That's the formula that will automatically do this entire thing out for you. Okay, so you need to know the formula for adding up when you have a constant here and when you have a k here. So these are the two formulas that are going to replace the sigma. Okay. And if you want, you can simplify that. All right. Like if we do this out, what's n times n?
N squared.
N squared. And what's n times 1?
N.
Plus n. So you could write it like that. That's the same thing. Or if you want to divide each of these by 2, you can also do that. Dividing by 2 is the same as multiplying by what? 1/2. So I would say for a lot of the problems that we do, it's going to be more efficient to remember it that way, even though that's exactly the same thing. 1/2 n squared plus 1/2 n. I always remember it as n times n plus 1 over 2, and then if I need to fix it, I just do that out. All right, so let's try an example with that. You're not going to have to worry about the squared or the cubed formula. Okay, just those two. All right, so let's try this. So to simplify that, let's look back at our formulas. And we want to look for either what I just circled in red in the problem or what I just circled in blue. We don't have either one of those. We have something a little bit more complicated. So what we have to do with that is take that sigma and break it apart into 2 sigmas, just like that. So we're going to take what's all combined, we're going to separate it. All right. So where we're going to separate it is right at that plus sign. So we're going to make a plus sign, and now we're going to write down 2 separate sigmas. There's 1. There's 2. Where does each sigma start? So we'll start at 1. Where is each sigma going to stop? N and N. Now, what's going to be the formula that goes right there for my first sigma? I'm going to have a negative 2k. And what's going to be the formula, or the thing that I put right there for my second sigma? 3. Yep, positive 3. Now, which one of those sigmas looks exactly like one of these?
The right one?
The right one. This one right here is one of these two rules directly. Which rule is it?
The first one?
Yeah, it's the first one. So we can get rid of this entire sigma now using that formula. Take the number on the right, multiply by what's on the top. So what does that sigma on the right turn into? Yes. Okay, so that's the first one gone. Now we got to get the second one gone. This one kind of looks like one of them, but it's not exact. Which one does it look like? It looks like the second one. The problem is you're not supposed to have a number in the second one. It's just supposed to be a k. So we have a number that's next to the k. Go back and look at this rule. What rule here allows us to take a number that's in front of a sequence and put it in front of the entire thing?
The third one?
The third one. You don't have to keep that number in front of it. You can put it in front of the whole thing. So let's do that. Take that number and put that in front of the entire thing. So you have -2. Write our sigma again. But now what's left to the right of that sigma? Just the k. And now look at that. Does that look like anything we have over here? Yeah, which one? The second one. So that's the goal, to try to take the sigma that they give you, break it apart, and make what you have always match one of these two. And once you do that, then you're going to substitute in. All right, so the +3n, we're just going to keep that there. -2, we're going to keep that. And now what I have circled right here, replace that with that. Because we know these two things that I just put an arrow between, they are exactly the same thing. So replace that with 1/2 n squared plus 1/2 n. And now we'll use the distributive property and do that out, but that's how you get rid of your sigmas. So now let's distribute. What's -2 times 1/2? -1. What's -2 times 1/2 again? -1. Okay, is there anything I can combine with that -1n squared? No. So we'll just leave that. How about -3n? I'm sorry, -n plus 3n.
Yeah.
Plus 2. Yeah. And that's your answer. So what does that answer do for you? Well, let's say that I wanted you to take this formula and add up every number from 1 to 5,000. If you didn't know how to do what we just did, you would have to start with 1, fill it in for k, write down what you get. Then go to 2, fill it in, write down what you get. Go to 3, 4, 5, all the way up to 5,000. So you'd have 5,000 steps. Then you'd have to take each answer that you got and just add them all up. Now, using this formula, if you want to know what the first 5,000 terms are going to add up to, all I have to do is fill the number 5,000 in on my calculator, there, and there. And it'll tell me the answer automatically. So it's a lot faster way to add things up. Let's try one more of those, but let's get rid of the squared because you guys aren't going to have any with squareds in them. Okay. All right. Does that directly look like rule 1 or rule 2?
No.
No. Then let's break it up. Okay, so break it up into 2 sigmas. Where does each sigma start? Where does each sigma stop? N. N. It's going to be a subtraction sign between them. What's going to be the first formula? 5K. Second formula? So what are you going to put in that box? 2. Because we already put the minus in front. Okay. Now, look at the one in blue and look at the one in red. Does either one of those match up with those rules? Yeah, the right one. We can simplify the right one. And what would it turn into?
2n.
2n. You're adding up the number 2 that many times. 2 plus 2 plus 2 plus 2. Okay, so we got that. Now, does the left one match up with any of these directly? Not quite, because there's something there that we don't want. We don't want the 5 there. So where can we put it? We can put it before it. If you put the 5 before it, basically end up with that. Right. Now, focus just on the part that's in the blue box. What does that blue box turn into? Yeah, it turns into 1/2 n squared plus 1/2 n. Okay. What's 5 times a half? Yep, so it's 2.5 n squared. And then what's 5 times a half again?
2.5.
2.5 n minus 2n. What's 2.5 n? Take away 2n. 0.5 n. Okay, so now if I wanted you to add up the first 1,000 numbers in this formula, instead of plugging in 1, 2, 3, 4, 5, all the way up to 1,000 for k, and writing them all down, all you have to do is, on your calculator, do 1,000 squared times 2.5 plus 500, whatever that comes out to. All right, so that's the idea of how you change something that has a sigma into something that doesn't. Any question on that? Okay. All right, and this is the last one. So the last one, that we're done with sigma. Okay, that's everything I wanted to show you. The last one basically is how do you add up terms in a geometric sequence? Like that one. I'll even write out one more. So it's times 1/3. So the next one would be 2 27ths. So each term is basically being multiplied by what here?
1/3.
Yeah, 1/3. That's your R value. I want to know if I wrote out the first 12, what would the first 12 add up to? But I only have the first 4. Okay, if I wanted to do the first 12, I'd have to multiply by 1/3, write that down. That's the 5th one. Multiply by 1/3, write that down. That's the 6th one. And then I got to keep going. Okay, it's going to take a while to write out all 12. Well, if you are multiplying by a number each time, you don't have to write down all the things you want to add up. There's a shortcut. The only thing you need to know is what are you multiplying by each time to get from one term to the next, and what term did you start with? That's enough information. What term did we start with here?
2.
Started with 2. Oh, and you do have to know where to stop, right? Otherwise, you just go on forever. How many are they telling us to add up? 12 of them. Okay, so that's your first term. R is what you multiply by. It says multiply, believe it or not. What you multiply by, and n is the number of terms to add. So if you wanted to add up the first 12 terms in that sequence, we don't even know all 12 yet, but we don't need to. Okay, what's the first term we're adding up? 2 times 1 minus, what did I multiply by each time to get from one to the next? 1/3. And how many terms are we adding up? 12. So that's going to be to the 12th power. And in the bottom, it's 1 minus 1/3. What's 1 minus 1/3?
2/3.
2/3. That's the answer. Right? We just have to, when we type that in, just be careful typing it in. Let's see what we get. Okay, because it's got a lot going on, I think I'm going to do it in a couple steps. Let's do the top first. 1 minus 1/3 to the 12th. Okay, that was enough that I don't think I messed anything up. So there's the top. Now divide that by 2/3. And the last thing is there's a times 2 in front. So if you add up the first 12 terms, it's 2.59s and then a 4. What does it look like it's getting pretty close to? Yeah, it's getting pretty close to 3. And even if you added up the first 100 terms in this particular pattern, it wouldn't go above 3. It's just going to keep getting closer and closer and closer to 3. And that's what we'll look at tomorrow, adding up even more than just 12, adding up an infinite amount. All right, any question on that? Okay, so the homework, it's all odds. It's 1 through 19. But I think there's one I might have you skip. We'll check. So it's 1 through 19 odd, but you can skip 9 and 11 because we didn't talk about how to do those. So just skip 9 and 11. All right, and we'll take a look at that tomorrow. And I plan on being after school tomorrow for extra help.